Yeah, hello. In this video, I will show you how to fit a multiple linear regression model using R, and also how to check confounding and test interactions. Okay. Now, first, let's set the random seed. Sample size is 100, and then we'll create two continuous independent variables, x1, x2. Both are from normal distributions. And then we create two categorical independent variables, x1, no, sorry, x3 with two levels, 0 and 1, x4 with three levels, a, b, and c. And both are created as a factor. And to create y, the dependent variable, we use this statement. So basically, y equals 5 plus 1.2 times x1 minus 0.8 times x2. And then we have if else to specify the value of x3 when x3 is coded as 0, then it's a 3. If it's a 1, it's a negative 3. For x4, if it's coded a, then its value is 2. If it's a b, coded negative 1, and otherwise it's c. And also there's the error term, which is from a normal distribution with mean 0, standard deviation 2. Okay. Then we put all these variables together into a data frame. So here's the first few rows of that data frame. And if you look at the structure of the data frame, you can see y, x1, x2 are numeric variables, and x3, x4 are factors. Okay. And to fit a multiple linear regression model, we use the function lm. So the syntax is lm, y tiered x1 plus x2 plus x3 and plus x4, data equal to data. Okay. So here, because x3, x4 are already factors, so we don't need, in front of x3, x4, we don't need to put the command factor in front of them. Okay. If they're numeric or other types, we may have to use the factor function to convert them into factor. Okay. And then we save the output into this object for the model. And if you want to look at the outputs, you can use the summary, the model. You can see it has some summaries of this model output. You get the call, which is the formula for the model, the 5-point statistic of the residuals, and then you have this coefficients table with the intercept and the variables, and you have the for the category variable you have the reference level not showing, but you have the other categories shown there. So beta estimate, standard error, t-value, and p-value, and they're marked as the star system there. Okay. And then you got the residual standard errors, degree of freedom, r squared, adjusted r squared, and also the f statistic and the p-value from the overall test, whether the model is actually significant or not. Okay, more significant than the intercept only model. Okay, and if you want to really look into the structure of this model object, you can see it's fairly complicated, and you have to spend some time. So it's a list of 13. Okay, so you have to go through the list to see what's in there. Okay, and also here I'm going to just show you the very basic residual plots relate to a fitted linear regression model. So here we can partition the graphic window into 2 by 2. So then you use a plot of model. You immediately get these 4 plots showing you the goodness of fit and the influential data points, and etc. etc. Okay. I have 2 videos comprehensively covering regression diagnostics. Okay, you can find them in my channel. So I'm not gonna do more coverage here. Okay. All right. So after you have fitted a multiple linear regression model, we know the advantage of multiple linear regression model is it allows us to really investigate the relationship between three or more variables. One of those relationships is potential confounding variables. Okay, so here, since we're using a synthetic data set, so I'm just arbitrarily saying, okay, we assume x1 is a potential confounder for the relationship from x2 to y, while controlling for x3 and x4. Okay, so to check the potential confounding, we need two models. One is the model one without x1. Okay, so we fit model without x1, and we have the summary there, and then you get the beta coefficient for the x2. Okay, and the model 2 is with x1, so you get a model with x1, and then you look at the summary and you get the beta coefficient for x2 in this model. And we can extract the coefficient by using the COEF, C-O-E-F, and then we're using this syntax to extract that beta coefficient without x1 and with x1. And then we can calculate the percentage of change, which is the absolute change multiplied by 100, and we can print it out. The rule of thumb is if this absolute change is above 15%, then it may indicate a potential confounding effect. Okay, so here in this hypothetical example, the absolute change is like 5.9, so it's a very, very strong potential confounding effect. Okay, but you know we're using a synthetic data set, so don't take this too seriously. Okay. So for confounding, there's no hypothesis test. We can only do checking using the absolute change, the absolute relative change of the beta coefficient, okay, with and without a potential confounder. But for interaction, we can actually do hypothesis test. So if, for example, if we want to test whether there's interaction between x2 and x3, then we can simply add x times x3 as an additional kind of the additional interaction term to the model, and then we can print out the summary, and you can see there's the mean effects model with x1, x2, x3, x4, and then there's the x2 and x3 interaction term. Here, the p-value is 0.96, so there's no significant interaction between x2 and x3. Okay. Then there's a shortcut if you really say, oh, I'm just doing, fishing for significant interaction terms. I want to look at all possible interactions between all these four independent variables. So you can use this formula. So x1, x2, x3, x4, parentheses squared. Okay, so let's fit that model of all interactions, and you print them out. You can see, in addition to the mean effect, you have all the interaction terms tested here. Let's see. None of the interaction terms are significant, so unfortunately they're not interacting. Okay. All right. So this is a really like a basic introduction to how to fit multiple linear regression using R.